Hi, this is lecture 29, and this is going to be another long example in which we're going to use energy and work together to figure out something. So the scenario here is an elevator that's falling. Imagine a cable has snapped and now the elevator, drawn here to perfection, is falling. I'll try to indicate in this diagram all the information that's going to be relevant that's given to us as part of the problem. So the mass of this whole thing, including everybody inside, is 500 kilograms. We pretend it's moving downwards at a speed of 4 meters per second at the instant when the cable breaks. And this is 12 meters above the ground. And there's a little bit of friction with the walls, but really 1,000 newtons, but really you're just falling on a crash in the ground and then you're dead. Well, lucky for us, some genius engineer decided to put a giant spring at the bottom. It's kind of a fail-safe system. Now, this is not what real fail-safes for elevators look like, but let's just pretend for right now we put a big spring. Here's like at the top of the spring, little platform. The elevator falls on it, and it squishes the spring, and that gradually slows down the elevator. It doesn't just crash, right? So here I've drawn it at the very lowest point. The elevator has fallen. Here's the ground level, but below ground it keeps going down till the spring is the most squished, most compressed. And let's pretend that this is 4 meters below ground level. So this spring is compressed by 4 meters at the lowest point. Our task is, from the data given here, is to figure out what is the spring constant. Remember, the spring constant is a measure of how tough is the spring. It's saying, well, how many newtons does the spring force, is the spring force equal to per meter of stretch or compression, right? So if I squish this by 1 meter, well, K is going to be how many newtons the spring pushes back with. If I squish it by 4 meters, it'd be 4 times as much, and so on. Let's solve this problem. So maybe what you should do right now is you pause this video and try to solve it yourself first. Right? You put all information that you need right here. Okay, so we're going to use energy to solve it. Hopefully you've paused, you've tried it yourself, you had a chance of having a go at it. So here's how we're going to do this. We're going to consider the energy at the beginning and the end, and we also notice that some energy will have been lost in the process. So I'm going to write this down. Energy. And at the end, I mean at the lowest point. Lowest point. What's it equal to? It's equal to energy at the beginning and then we're going to add to that the work done by non-conservative forces. So non-conservative forces being those forces that don't have a potential energy associated with them that we could include in these terms. Right? And if I look at this diagram, the non-conservative force here is going to be the friction. Realistically, there might also be air resistance, but air resistance is a little bit more complicated to deal with because it depends on the velocity. And so actually doing calculations with it, like what's the work done due to air resistance, would require us to solve some differential equations. You might do that in a more advanced course on mechanics. So we're going to deal with friction, which is a constant force in this case. Work done by friction, we know, is going to be negative. So we're really subtracting energy due to friction, which turns mechanical energy into thermal energy, right? It warms up. Friction, rub your hands together. Friction, it warms up your hands. Okay, so why am I writing this down? Well, just so I have a kind of intuition of what's going to happen. So I can, as I do my calculation, do little sanity checks along the way to make sure I'm still on the right track. For example, if I find that the work done by friction is positive, I know I must have made a mistake somewhere, because I know friction should be slowing stuff down, taking energy, mechanical energy out of the system. Alright, So let's start by looking at those three terms separately. So the energy, it's not the energy at the beginning. By beginning, I of course mean the instant the cable snaps. Let's go back to the picture. We are up here. We have a certain height above the ground, and we have a certain cruising speed. So the cruising speed is going to give me some kinetic energy. Then there's gravitational potential energy. And I have to make a choice where I pick my zero height. I could pick it anywhere, as always, but I think I'm going to go with the most intuitive idea. I think it's to pick the ground level, and actually it's going to be a nice choice, because it's also the zero compression point of the spring. So I kind of anticipate here, hey, that's probably going to make my math easiest, because the ground level is not just in arbitrary zero, it's also where the spring is essentially at rest, at its natural length. Alright, so let's get started. I'm going to work symbolically, so I guess I should really label my different quantities with symbolically. So I'm going to call my initial speed simply VI for initial. The force of friction, let's call this FR, friction. The height, let's call it H. The maximum compression of the spring, I'm not sure what to call it. I'm going to call it D, or some other distance. And the mass we're going to call M. I think that's all the quantities we need. Okay. So my energy at the beginning is 1/2 mv initial squared, right? Because that's the speed at the beginning. I'm going to add to it m, the mass of the elevator, times g, times our height from the 0 point here. Okay, that's h, the little h. So it happens to be mgh, the kind of expression you might just remember off the top of your head. Note though that h here is specifically the height from the ground, which I happen to have denoted by little h. If you pick your 0 point, say down the lowest point of the spring, you would have put in d plus h. Make sure you understand that. So that's that. Then at the end, I have, well, I'm all the way down here. So what do I have? Well, it's going to be the lowest point. So this is where the elevator stops. So there's 0 kinetic energy. I'm going to write this down, 0, and I'm going to put underneath kinetic energy. Why am I doing this? It's just 0. Just to remind myself that I've taken care of the kinetic energy. Okay, so where are we? We're down here. So the spring is compressed, right, by 4 meters. Distance d. So the spring potential energy is 1/2 times the spring constant times d squared, because that's the distance of compression. This expression 1/2 k times compression or stretch distance squared, being the potential energy of a spring. Well, we've talked about this before as an example. This is my elastic or my spring potential energy. Oh, did I forget a spring potential energy here? I guess so. I could put just a 0 here, because the spring, of course, at the beginning is neither stretched nor squished. So don't make the mistake of just blindly plugging in, oh, we are height h, right? Well, the elevator isn't attached to the spring. The spring isn't stretched up to here. It's not glued to the bottom of the elevator. Right now, the spring is in its natural state, has no energy associated with it. So is this it? Actually, well, we are down here, so we are below ground, so we have to take into account the potential energy change from here down to here, the gravitational potential energy change, because we're still going down. So I'm going to have plus mg the height, except what is the height? The height is minus d, right? I'm that far below ground. D is the distance, literally just 4 meters. I know it's minus because I'm below ground. I'm 4 meters underneath my 0 line. Am I setting those two equal? No, because some energy is lost in the process. So that's the last piece. We need the work done by friction, because we can't account for friction via potential energy, because it depends on the path. But it's still fairly easy. It's just the force times displacement, force of friction times displacement. Displacement being, of course, well, not of course. What is the distance? How far has the elevator moved? It moved from up here all the way down here, and it still kept moving down here. So the displacement from beginning to end is h plus d downwards. Right? Now the force of friction is upwards, so if this is a positive displacement, this is a negative force. Now I could just leave it like that and have the minus sign be implicit, like being contained in here, but I'm worried I might get confused. So what I'm going to do, I'm just going to write it like this. The absolute value, 1000 Newton, put a minus in front. And that way I can be sure, okay, it's minus, it's negative 1000 newtons, that's just the absolute value. The sign is taken into account separately, times displacement. This isn't how you have to do it, but I find this a useful way to make sure I'm not getting confused by the signs. I'm separating the value from the direction. Okay. What are we trying to find? All right, the spring constant. But now we can put the pieces together. Energy at the end is what you start with, plus the change due to other forces. So let's write this down. I have 1/2 k d squared plus, minus mgd, that being equal to what we start with, 1/2 mvi squared plus mgh, and then go to add this, so minus the magnitude of the force of friction times h plus d. So at this point all the quantities are known, except k, which I can solve for. But everything else is given. Looks like a long, series of expressions, lots of symbols, but all the quantities here are given. So I can easily rearrange it. I'm going to find that k is equal to, I'm going to multiply everything by 2, divide everything by d squared to isolate the k, times the rest. Now I suggest that you work through the rearrangement yourself, the algebra yourself, if you haven't done this already. Times h plus d. And now at this point, all that is left is to literally plug in the values. Now please do it yourself. What I find when I'm doing this, so d is 4 meters, m 500 kilograms, you work it all out. The answer I come to is 8,500 newtons per meter. Now just to give you some intermediate values, if we had plugged in numbers earlier just to see where we are at, the initial kinetic energy, half mv squared, would have been half times 500 times 4 squared, that's 4,000 joules. The initial gravitational potential energy, 500 times 10 times 12, that's 60,000. So a lot more potential than kinetic. Excuse me. In the end, of course, this one we can't evaluate because k wasn't known, but this quantity here, 500 times 10 times minus 4, so it's 5,000, it's minus 20,000 joules in all cases. And what's the work done by friction? How much energy is lost there? Well, it was 1,000 times h plus d, 12 plus 4, 16. So this whole thing is minus 16,000 joules. So I start with 64,000 joules. I lose 16,000 to friction overall. The potential energy then is 20,000, which means this term here would be 64 minus 16 plus 20, that's 68,000. And I could just have 68,000 here, and then I plug in values, and that takes you there. So make sure again, if you didn't work it out at the beginning, you pause the video now and try the calculation again yourself to make sure you can keep track of all the terms and you understand where each one comes from. Because a lot of those problems are really just identify what interactions are relevant, how you can take them into account via potential energy or via work, and then put the pieces together. That's pretty much all there is to it. Let's do a little bonus question. Just remind ourselves of stuff we learned before. The bonus question is, how heavy do you feel if you're inside the elevator at the very bottom just as you come to a stop? How heavy do you feel at the time, at the moment, the instant the elevator comes to rest? Of course, how heavy you feel, well, it's going to change throughout. You're going to be almost in free fall initially. There's a bit of friction, so not quite. You probably feel very light then. But then as you get slowed down by the spring, you probably feel very heavy. So again, pause the video, try to figure it out. Maybe you have to look back at what you learned about the perceived weight. So pause the video and do that. Okay, I assume you've tried it yourself now. If not, your loss. So what am I trying to find? I'm trying to figure out my perceived weight. How heavy do I feel? Well, that is to say, we want the normal force. Right? The normal force on your body, that is how heavy you feel. When you stand on the ground, you feel your normal weight because normal force is equal to your weight. When you're in free fall, you feel nothing. You feel weightless because there's no normal force, even though there's a weight. Remember, that was what you actually feel is the internal normal forces of the different part of your body pushing against each other. So how am I going to find this? Well, I'm going to find the acceleration. Find the acceleration A at the bottom. That's what I want to do. Well, I can find the acceleration of the elevator, and that's also going to the acceleration of anyone inside the elevator. So at the bottom, the spring compression is equal to D, which is 4 meters. Now, we worked out a spring constant K is 8,500 newtons per meter. But it tells you the force per distance, per compression. So there's the spring force, F spring, and that's only the very bottom, when the spring is all the way squished. It's going to be 4 times 8,500 newtons per meter. I've got 4 meters. And that comes to 34,000 newtons. Of course, that's not the force on you. That would kill you instantly. That is the force on the elevator. Well, can I find the deceleration, as it were, from there? Is this the only force acting? No, there's also the spring force and the weight, right? So at the very bottom, the elevator still has a weight. My free body diagram for the elevator. Let me write this down so we don't get confused. It has a force of friction that's upwards, and it has the spring force. The spring force is going to be probably pretty big, so F spring. So those are the forces right at the bottom as the elevator comes to rest. So the mass of the elevator, I think I used little m for the mass, A, in second law that I'm writing down, is going to be F spring, F friction over mg. Actually, I only really care about the magnitudes now, right? I want to find the acceleration. So the magnitude of the acceleration. So I'm going to just work like this. Absolute value of the acceleration. Because I know really this ought to be like negative, but I want to know, you know, what's the net force, how many newtons, not which direction. I know which direction it's up. It's going to be the spring force. Add the friction. They work together to slow down the elevator. And then I want to subtract the weight. So I can plug in all those values, right? We know what this one is. This is 34,000 newtons. This one is 1,000. It hardly makes any difference at all. And this one is going to be 5,000 newtons. Why? Mass 500, G 10, 5,000 newtons. So that's equal to 34,000, 35,000 minus 5, 30,000. That's the net force equal to MA. That implies A is going to be 30,000 newtons divided by the mass. The mass is 500 kilograms. Right, this is my M. We at M. That comes to 60 meters per second squared. So that's a lot. That acceleration, you can already anticipate, is probably going to hurt. Right? It's 6 times the acceleration due to gravity, but actually it's survivable. It's going to hurt, but you're going to be okay, probably. So because it only acts for a split second. So what's normal force on you? Well, I know that my acceleration, m, me, is, I don't know what my mass is. I don't actually care. You can define it, it's my mass. And now let's draw me, my free body diagram. Well, the spring doesn't act on me. The spring acts on the elevator. What acts on me is the normal force. I have a weight down. My mass of me. And I've got a normal force from the floor. Now it's going to be bigger because I'm going down and it's slowing me down. And that is the quantity that's going to tell me about how heavy I feel. So the normal force, let's call it F subscript N for normal force. Well, what I know is that Fn minus, the weight of course is not the mass times g. If you were confused, then good on you, it means you're paying attention. Minus my mass and me times g. That's equal to, well, now the object is me, so it's going to be my mass times A, but the A is the same value that we had before. Now, I actually know that the A, right, I can write A, it's 60 meters per second, second squared. I'm going to write this as 6 times G. How people talk about G forces and so on. You express something in acceleration in multiples of G, or a force in multiples of your own weight. Right? G is 10, so 60 is 6 times G. Why am I doing this? Because then I can conveniently write the normal force as this plus this. My weight plus 6 times my weight. Right? Because this goes over here, becomes plus. This is 6 times my mass times G. Add once my mass times G. It's 7 my mass times G. So I feel 7 times heavier. Oh dear. Now that is going to hurt. But it's only for a split second at the very end. Before that, the spring isn't quite so squished, so actually acceleration is a little bit less when the spring is, say, half squished, right? So if I go back to the picture for a second, not all the way at the bottom yet, you're sort of halfway like here. The spring is a bit squished, but the spring force is not going to be as large, so your deceleration is not as large. So it's only at the very end that you get this. This is like the maximum force, maximum perceived weight you have to endure, and the whole thing doesn't last very long. So you probably survive. But it'll hurt, you get some bruises. So if you say a fighter pilot, you might well expect to experience this when you're engaged in some kind of air battle with tight, super fast, tight turns in your plane and so on. But you can't endure this kind of acceleration for any extended period of time. The human body just can't cope. You'd pass out and eventually die. But here it's only for a split second, so you'll survive. Good job. But you might get some bruises. Hopefully this last part was a nice little review of some concepts we did earlier, and hopefully it reminded you that if you were unsure about this, you should go back. Physics builds on itself. You can't really forget what you've learned before. Alright, I'll see you in the next lecture.